So hopefully you're keeping up in these videos. I mean, again, I realize there's a lot to talk about, especially for something that's not required in the course. But to kind of recap at this point, organic molecules absorb light because electrons promote it from the HOMO to the LUMO, and this is the primary color we see absorbed by the molecule. Now, why does this correspond? Why do we care about this in terms of azochemistry? So what I want to focus on here on methane is the HOMO and the LUMO. So we're going to ignore the carbon 1s, even though it does play a role. Well, the actual energy difference between these two corresponds to basically the differences in electronegativities between the atoms, as well as how well they overlap. So if we have two atoms with the same electronegativity like we did in hydrogen, we get a gap, but it's not a huge gap. As we start stabilizing the electrons more and more, so we start working with more and more electronegative elements. So if we were to switch from hydrogen to fluorine, this would further lower the energy of the bonding orbital and increase the energy of the antibonding orbital. The reason being is that the driving force to move those electrons from carbon to fluorine is those electronegativities. So by going to these more electronegative elements, you end up driving the orbitals down. Now, there is a caveat on this. You still have to have good overlap between the two atoms. So if we were to switch from something like carbon to fluorine, fluorine is a bigger atom. Its electron orbitals are more diffuse. So it's harder for silicon to bond to fluorine. It does, but the bonds aren't as stable as something like carbon fluorine, because carbon fluorine, they're basically the same sizes, so you get really good overlap. When it comes to silicon, it's so big and it's so diffuse, that tiny fluorine atom can't really overlap with a lot of that electron density. So yeah, there is a little caveat on there. But generally speaking, as we increase electronegativity, we're going to drive down the energy of the bonding orbitals and increase the energy of the anti-bonding orbitals. And this is going to increase the difference between the HOMO and LUMO, which means that we're going to start increasing the energy of the light that is absorbed by this molecule. So this is going to start giving rise to what we can do with azochemistry. So let's start talking in the next video about a simple azide dye. So this dibenzene azide, and talk about how adding electron withdrawing and donating groups are really going to begin to affect the color of this molecule.